right. Hello, everyone, and welcome to Proteins and Peptides Part 3. This will be Section 3B. And what we're going to talk about today are something called peptidomimetics. So what are peptidomimetics? Why are they important? How do we make them? And how can they be used to solve questions? So again, this is the outline. This is Part B. What are peptidomimetics? Okay, so peptidomimetics, as the name suggests, are mimics of peptides. Okay, so they contain a lot of the same structural elements, perhaps things like peptide bonds, maybe some of the same R groups that we've seen for amino acids, and or they also may contain unusual functional groups. So they're like a peptide, but they differ in structure slightly. The molecules can vary in size and structure, so you can have small peptidomimetics or large peptidomimetics. And as we learn in part 2, we use a Merrifield resin to conduct solid phase peptide synthesis, and we can also use the same type of approach to generate peptidomimetics and to therefore study structure-activity relationships. This is also a very excellent way to find lead compounds for possible drug and or medicinal candidates, and we'll touch upon that later in this unit. Okay, so let's look at some common peptidomimetics. All right, well, before we start, let's look at our baseline peptide, which is the first structure shown here. So what you see here is a regular peptide with L amino acids interspersed with our amide bond. So this is our good friend, our regular L peptide. Okay, and as you know, L peptides are comprised of alpha amino acids. So there's a carbon of interest and the carbon adjacent to it is alpha. So if we look at this structure down here, so let's just call this A. If we look at structure B, you can see here that you have R groups R1, R2, R3, but you have an additional carbon, okay, between the R side chain and the carbonyl group. So if this is our alpha carbon, this is now called a beta carbon. This is alpha, beta. So this would be called a beta peptide. And beta peptides are interesting. They're mainly unnatural. There are some exceptions where some beta peptides or some beta amino acids are used naturally, but in general, they are unnatural. Some of the advantages of using a potential beta peptide is that that additional carbon here gives it a little more added hydrophobicity. So you can get slightly different structures. You can get different shapes of peptides and different stability. Furthermore, these peptides here are not proteolithically degraded by proteases, so they're not recognized, by the proteases that degrade them. So from a therapeutic point of view, these ones could be advantageous. So they're proteolytically stable, and they can give rise to different structures, secondary structures, and different thermal stability. One of the drawbacks to beta peptides, however, is the presence that they are not naturally abundant. They are difficult to synthesize. So to buy the basic beta peptide amino acid building blocks usually requires some significant investment in money, whereas L peptides are fairly inexpensive. So moving on, if we look at structure C, you can see here that it looks very much like A, except we have inverted the stereochemistry, and in fact, it's a mirror image of A. So here you have regular L peptide, here you have unnatural D peptide. Okay, so we live in a world of L amino acids. However, You can use chemistry to synthesize dipeptides. Um, Again, there are some natural sources of D-amino acids, however, they are quite rare. And again, one of the advantages of using a natural dipeptide would be that proteases would not actually be able to recognize them. So they would be actually quite stable in a cellular environment. You would expect to get the same type of structures as L-peptides, except it would actually be the mirror image. So, and at the end of this unit, there's actually a very interesting application in which researchers used dipeptides to solve a particular structure. Because they're a natural and they're stereospecific, these ones are actually quite expensive to make. The last class of peptidomimetics down here is quite different. It's probably the most different from the other two. And what you can see here is that you have this carbon here with nothing on it except two hydrogens. And you have your R groups, which instead of being placed on the carbon, is actually attached to the nitrogen. So you have R1, R2, R3, R4, R5, etc. So yeah, we could put R4 here, or it could be just a hydrogen like lysine. So please note that the R chains, R groups, they're on the nitrogen. And this actually is a structure that's called a peptoid. Okay, peptoid. Peptoids are quite different. They can have very unusual secondary structures. They can be very stable, and they can actually be very good building block for generating libraries of compounds. So they can serve as a very excellent way to make peptidomimetics. They're pretty relatively easy to synthesize, and we'll go through that synthesis in just a moment. So they can have unusual secondary structures. One of the drawbacks with peptoids is that by removing this NH group from peptides and beta peptides, as I'm showing you here, you actually lose some hydrogen bond capabilities with solvents or other interactions that I might want a hydrogen bond with. So peptoids often can have problems with solubility, especially if your R groups, R1, R2, R3 are quite hydrophobic. So they can be insoluble. So this can sometimes pose some challenges if you're trying to do experiments in aqueous solution. All right, just one last thing is that these are also stable. They're proteolytically stable. And peptoids are also relatively inexpensive. So I'll just put one single dollar sign there. All right, so let's look at how we can make peptoids. Solid phase synthesis of peptoids. So what's really nice about peptoids in general is that synthesis itself doesn't usually require protecting groups. So you avoid that complexity of adding them to monomers beforehand and then removing them at each step of chain synthesis. So you'll see in a moment that the synthesis is actually much simpler. And like we've seen before with peptides, you get chain cleavage and deprotection. They can occur under mild conditions. So let's start with our Merrifield resin. And what I will do is I will sort of show an example where we are already starting with an R group attached to a peptoid. And then what we're going to do is grow off of it. So you can imagine the solid phase resin has all of these amines with this R group attached to it. And so what we're going to do in order to generate this peptoid is we're going to incubate this with a compound called bromoacetic acid, which looks like this. And bromoacetic acid, when we incubate that with a coupling agent, let's use HBTU, what you know is that this acid will get activated, form an active ester, and then the nitrogen, which is an amine here, will come in and form an amide. So there's nothing really new here about the chemistry. Okay, so there's your R1, and now you form an amide, and then you have this alpha halide group attached here. Okay, so let's call that step 1. Step 2 is now the introduction of this new nitrogen R group. So at this stage here, what we're going to do is we're going to react this with a primary amine, and attached to the primary amine is going to be an R group. Okay, so you can imagine that could be like NH2CH3, NH2 phenyl group, you know, really whatever you want or whatever you're trying to make. And many amines are commercially available. So these are actually quite inexpensive, and there's a large library of them available. So what you can see here is that in terms of the mechanism, you can imagine this will come here and you'll do direct SN2 substitution. So what you'll end up generating is now your R2 peptoid on the growing chain. So at this stage here, we've done 2 steps. First one, amide bond, formation by coupling the amine with HBTU and the bromoacetic acid. Number 2, you take the halide, alkyl halide, with a desired amine via SN1. Via SN2. And then at this stage here, what you do is, if you want to keep growing your peptoid, you can see, just go back to step 1, right? So now you need to add the bromoacetic acid with HBTU. Right, and then you add your desired primary amine, and this just repeats itself over and over again for as long as you want. So step 3 is repeat 1 plus 2, steps 1 and 2, until desired peptoid then cleave from the resin. Okay, so it's a fairly simple iterative process. Okay, so let's actually make a peptoid. All right, so here's a peptoid that we want to make. Okay, so the first thing we want to do is look at where, you know, the N terminus and the C terminus of this peptoid is. So as you can see from the left, this over here is our N terminus, the nitrogen, and over here on the right is our C terminus. Okay, so what we're going to do too is we're going to start off with our Merrifield resin, like we learned last unit, where you have that styrene and the halide, the chlorinated styrene, and then we activate that with our precursor. So in order to get this activated, the first thing we're going to do is we're going to react this with bromoacetic acid. Now you might say, well, why are we doing that? Because bromoacetic acid, in the last time we did that, we actually coupled that to a nitrogen amine, right? In this case, we're not doing that. What we're doing is we're doing an SN2 reaction in which a triethylamine will deprotonate to give you a carboxylate, and then this will nucleophilically attack this group via SN2. Okay, so this is used in the first step very differently. So you do not add a coupling agent to this. Okay, once we do that, we now have our ester formed between the Merrifield resin and now this alkyl bromohalide. Okay, so now at this stage we can start adding our specific amine groups. So as you can see here, we're growing the chain from the C-terminal end all the way to the N-terminal end, right? We've put on our C-terminus at this area here. So we're going to be going in this direction in terms of the direction of synthesis. Okay, so what are we going to add as our next chemical? Okay, so you can imagine up here you have your bromine attached. So now we need to add the nitrogen. So you can see I'm circling it with my pen. I'm not writing it in, but you're basically going to add this group here, this isopropylamine group, as a primary amine. Okay, so this group will add via standard SN2. And what you will have is this group right here. Okay, so we've built it all the way up to here so far. All right, so now you can see the pattern that we learned on the previous slide. So now we need to form an amide bond, and we're going to react this with the bromoacetic acid and coupling reagent. Okay, so step 3 will be the bromoacetic acid and coupling reagent. Okay, step 4 will be the amine here. This is called ethanolamine. Okay, and now ethanolamine would have an H here, but to prevent the hydroxyl group from acting as an undesired nucleophile, we want to protect it, and we're going to use something called tert-butyl silyl-protecting group. Okay, so TBS group. It's a silicon protecting group, and it's going to prevent that undesired attack, and we have seen that before. The next group, therefore, is going to be another molecule of bromoacetic acid, right? So now we're constructing this portion up here. And then after that, you can see here that you have this phenylamine, right? So that'll be step 6. And just to reiterate, the real nice advantage of doing this in solid phase is that you do these SN2 reactions or coupling reactions, and then you just wash all the excess off, and the desired chemistry stays on the bead. So it's really quite efficient and quite easy. Then nextly, we're going to add one more unit of this bromoacetic acid. Okay, so we are at this unit here. And then you can see the last portion that we need to add here is this methylamine, CH3 and H2. Okay, so I've kind of put all those steps together one by one. And what we have, I'll draw this, is that we still have it attached to the resin. Okay, so what you have is this compound here. And the last thing we need to do now is we need to remove this from the Merrifield resin. So the one of the sort of the best ways to do that, like we learned with Merrifield resin, not rink amide, but Merrifield resin, is to actually use hydrofluoric acid. Okay, that will cleave off this ester bond here. And in addition, the HF will remove the silyl TBS protecting group. Okay, so hydrofluoric acid. Removes TBS group and cleaves peptoid from the resin. Okay, so now I hope that you can appreciate that peptides can be made efficiently in lab. Also, peptoids can be made efficiently in lab. So this is actually quite often used in the drug discovery process. So what I'm just going to talk to you about for the next few minutes are some peptide analogs of some peptides that have been very good at being potential drug candidates. Okay, so peptide analogs. So recently, there have been really good developments in the modification of peptides, particularly antimicrobial peptides. So what are antimicrobial peptides? So they are amino acids. They are peptides that are 15 to 30 amino acids in length, so not too long. It's certainly something you could make in lab, but these are actually produced naturally by all animals. We make them, insects, frogs, even unicellular eukaryotic organisms will make these. And often it's a first line of defense against microbial organisms. And as many of you have heard about antibiotic resistance, which is a growing concern today, the question is, well, should we or can we develop new antimicrobial peptides so that microbes cannot sort of develop resistance to these? And really, this comes down to something known as molecular diversity. What do these antimicrobial peptides look like? How do they function? And how can we design mimetics of them to overcome antibiotic resistance? All right, so let's take a closer look. All right, so antimicrobial peptides, so they're not too large, as I said, but they are these helical motifs that really form these alpha helices, as you can see here. And what happens is that there's a large proportion of hydrophobic residues, and there's also a large proportion of positively charged residues, okay? Positively charged residues like lysine, arginine, and histidine. And the way that they arrange themselves when they form helices is that you often have hydrophobic amino acids on one side of the face, whereas you have a positively charged amino acid on another side of the face. So the positively charged amino acids, this really helps embed itself within the negatively charged phospholipid bilayer. So you get that negative positive attraction. And then furthermore, the arrangement of these amino acids allow for bacterial membranes to become, they puncture it, and then they add this like hydrophobic pocket, which allows them to, is literally, as you can see here, punctures the membrane, and that causes sort of rupture and causes the bacteria to die. So if we look a little more closely at the structure of an antimicrobial peptide, it's actually called meguanine. And what they notice is that all the hydrophobic amino acids, so leucine, alanine, glycine, valine, isoleucine, they were all directed on one side, okay? Whereas a lot of the polar amino acids, like we talked about lysine, histidine, even some negatively charged one like glutamic acid, those were on the other side. So what you end up having is you have this polar surface, and then you have this hydrophobic surface. Okay, so this is a natural structure that insects and frogs and we make as well. But like I said, we've developed some, or bacteria have developed antimicrobial resistance. So the question is, well, can we retain that same structure, but maybe increase the stability of it? Can we develop other analogs that might have sort of this repeating unit of hydrophobicity and positively charged structure? So what I'm showing you down here is an unnatural structure, but you have these positively charged cyclic amino groups interspersed with these kind of hydrophobic cyclopentane type rings. So this would be an interesting candidate based on sort of a beta amino acid. So it's called beta 17. Another way to potentially increase the stability and the structure of this is to use something called fluorinated amino acids. Okay, so I'll come back to the slide in a second. But what are fluorinated amino acids? Well, fluorinated amino acids are synthetic, analogs of regular amino acids, except that they are comprised of carbon-fluorine bonds and are extremely strong. So everyone here, I'm sure, has heard of Teflon in their, you might have a Teflon frying pan at home, or you might have like Teflon coated, like a rain jacket or something like this. And really, what does Teflon look like? Teflon is a polymer that looks like this. It's a polytetrafluoroethylene polymer. Often abbreviated as PTFE. So these carbon-fluoride bonds are actually really, really stable. They're resistant to heat, and if you've ever cooked anything on these, food just doesn't stick to it, and they last a very, very long time. So Teflon is a synthetic polymer made of carbon-fluorine bonds. And the reason you get this really strong stability is because carbon-fluorine bonds are actually extremely strong. One of the strongest bonds out there. So if I go back to the slide here, what some researchers did is they added cis-fluorination on these hydrophobic residues here. So a typical alanine would look like this, where you have a CH3 group. Okay, so here's your CH3 group. So researchers replace those CH3 groups with CF3 groups. And that gave it inherent stability and some unique structures as well. So what they noticed, so they did that for leucine, alanine, glycine, valine, and isoleucine. So anytime there was a CH bond with those R groups, they replace it with a CF3 group. So for instance, glycine usually has two H's, so these were replaced with two fluorines. So what they noticed was that they developed something called Teflon peptide fluorogynin-1. It's a fluorous analog of the antimicrobial peptide meguinin, isolated from the skin of frogs. They replaced the hydrophobic residues with fluorinated versions to make them Teflon-like. And what was really interesting was that these resulted in more stable peptides. These are unnatural amino acids, right? We don't make fluorinated amino acids, but these stable peptides were more resistant to unfolding by chemical denatures and heat, and NMR also showed higher structural integrity. So this was really quite interesting. These results also indicated increased antimicrobial activity. So when these were used in the biological system and studying their activity, they saw that these molecules were more potent, likely due to the increased hydrophobicity of the peptide. Having that ability to stabilize the hydrophobicity and puncture that membrane even more makes it more attractive. And also, the strong hydrophobic interaction may make the peptide less susceptible to proteases. So proteases, we talked about this a little bit earlier, those degrade peptides. But if you have a fluorinated one, perhaps that will make these more resistant to proteases. Okay, so this is an example of peptomimetic incorporating fluorines. And the power of solid phase peptide synthesis allows researchers to put these amino acids in a controlled fashion. So that's one example. The last example I want to talk to you about today, this is the last slide, the other amazing advantage of chemical peptide synthesis. All right, so I want to tell you about this protein here called HIV protease. So HIV is a virus, as many of you know, and there's a specific protein from the genome of HIV that's a protease, and a protease is something that cuts a protein. Anyways, this protease is essential for the virus life cycle. Okay, so you can think of it as one of the essential proteins that HIV has to make in order to cleave a particular peptide bond in order for the life cycle to survive. So researchers have viewed this as a potential drug candidate, as a potential way to screen molecules because of its importance, essential for the virus life cycle. So for many years, researchers were trying to study the structure of this using crystallography or NMR, because if they could get the three-dimensional structure, then they could start designing molecules that could bind and inhibit it. And one of the attractive features too was that this is a fairly small protein compared to other ones. It's less than 100 residues, 99 amino acids in length. So what was interesting is that you could actually make this on solid phase synthesis. And you know, you might say, well, 99 amino acids is still pretty long, and you're right, but then you could actually make these in two portions and then use native chemical ligation to generate the desired compound. So researchers made a lot of this protease, and you know, for those of you who have maybe learned a little bit about crystallography or protein crystallography, it can be very challenging to generate crystals. It really just depends on the type of molecule you're working with, but oftentimes it's hard to predict how easy or difficult it'll be to crystallize. And so researchers tried to crystallize this protein for a really long time. And so anyways, later on, there was a technique called racemic protein crystallography, which really allows proteins to crystallize when they are in the presence of their racemic form. Okay, so people have done this with small molecules, and so researchers thought, well, what if we take the L peptide, right, of this HIV protease, which you could make either chemically or by recombinant techniques. And if you incubate that with the D peptide, could we generate racemic protein structures? And to generate the D peptide, because those are all unnatural amino acids, you could only do that using solid phase peptide synthesis. Okay, so researchers took these two together and they were able to incubate them together and finally observe a high resolution structure. So what you can see on my left is actually an image of the HIV protease in both its L form and its mirror structure form. And from there, they could get really important and useful knowledge about how to target this enzyme. Okay, so that's just another amazing thing about chemical peptide synthesis. Okay, so that's it for part 3B of proteins and peptides. See you next time.